Okay, so let's look at activity number 17 then. The first one, the distribution to the right. Okay, so there's that image there, that picture. That one's a lot like one of the ones you ran into on one of the exams, right? So let's take a look at that one real quick. So we're given this image that we have a normal distribution. We have a value of 35 right there and a value of A there. We're told that the area between those two values is 27.8. This area right in here is 27.8%. And we're given the mean and standard deviation of this distribution. So the mean is 39.3 and the standard deviation is 7.5. Right, this is some random variable x. And so we want to find the value A that would represent that. Okay, so what do we do to solve for this one? How do we find A? We need to find the area to the left of 35. Yeah, we find that area right in there. Let's put this in red maybe. If we find the area to the left of 35, we can do that. And then once we find that area, we will add the red area and the blue area together. And that'll give us all the area to the left of capital A. And then we can use our calculator to find the result of that. Right? So the red area, let's call that area W. So W is equal to the probability that X is less than or equal to 35, which is going to be equal to normal CDF negative infinity up through 35 with a mean of 39.3 and a standard deviation of 7.5. Okay, so let's figure out what that is. Normal CDF. Remember, for negative infinity, we just put a bunch of 9s, comma 35, comma 39.3, comma 7.5, close parentheses. I'm getting like 2832. This area is 2832, 0.2832. Okay. Now this guy up here is 0.2832. So now I add those two together. Now the area to the left of capital A is the sum of 0.2832 plus 0.278. So we add those two, we'll find the area to the left. I get 5612. And so now capital A is going to be equal to our calculator function of inverse norm, and it's 0.5612, 0.5612, which is the sum of those two areas, 0.5612. And the mean standard deviation of this distribution is 39.3, standard deviation of 7.5, and that'll give us my results. of 40.455. Any questions about that? No? Okay, that's the first one in the activity. Okay, what about the second one? The second one says, according to creditcards.com, 29% of adult Americans do not own a credit card. A simple random sample of 850 adult Americans is taken. Verify the distribution verify the distribution of the sample proportions is approximately normal. How do we verify it? What are the conditions that are required? In order for a sampling distribution to be approximately normal, what do we need? What do you think about that? Let me just draw the quick little picture that goes along with this. We have some sort of a parent population, which is all Americans. And then there is some proportion of Americans, P, that do not own a credit card, and so we're told that that's equal to 29%. So 29% of all Americans do not own a credit card. And now if we take samples, now how big are the samples going to have to be in this case? Size n equals to 850. Okay, so if we take samples of size 850, random samples from that population, every single time we take a sample, we're going to have a sample proportion, right? Maybe one proportion is going to be 31%. Maybe another sample proportion is going to be maybe 28%, right? Every single one's going to be different based on the sample and the actual values you get in your sample. And we know that when we graph all these samples, we graph all those samples, we end up getting a normal distribution. So this is a normal sampling distribution of proportions. So each one of these little dots along the horizontal axis is a p hat. It's one of these values. And we know that the center of this distribution, mu sub p hat, is equal to p, which is equal to that proportion up there. And we know that sigma sub p hat is equal to p times q divided by n, and then it's the square root of that whole thing. So in our case, this is going to be equal to 0.29. It's centered right in the middle at 0.29%, which is that proportion. And the standard deviation is going to be equal to 0.29 times q, which in this case would be 71, all over 850. And we take the square root of that whole thing. Okay, so let's figure out what that is. Uh, 0157, that's what I'm getting. 0.0157. Okay, and we are guaranteed that this is going to all work out, and this will be a nice normal distribution, and the mean and standard deviation will be derived by these equations, as long as, now this is the part where we have to check the criteria. There are two things we have to know in order to guarantee that this happens. One is that the sample size must be less than 5% of the population. It's got to be small relative to the population where you're drawing it from. Okay, so less than 5%. So is 850 less than 5% of all Americans? Yeah, it definitely is, right? So from this word problem, that criteria should be pretty straightforward. So all you have to do as far as show that the criteria has been met, which is that question there, all you have to do is say 850 is definitely less than 0.05 of all Americans. That makes sense. Okay, and what's the other condition that has to be satisfied in order for this to work out? Get a nice, pretty sampling distribution this way. P times Q times N must be greater than or equal to 10. Okay, condition number 2 must be that 850 times 0.29 times 0.71 must be greater than or equal to 10. If that's not true, then we can't solve it this way. We'd have to go to a different math class and learn a different method, because we don't have the tools necessary to solve this one in this stat class. Okay, so that's 175.015 greater than or equal to 10. Yup, it worked out. Okay, so this will be a case where when we do sampling this way of size 850, we will get this nice normal sampling distribution. Any questions on that? So the answer to part A, verify the distribution of the sample proportion is approximately normal. That was this. That's what you're supposed to write down there. Okay. Now it says find the standard deviation of the sample proportion distribution. Well, we already did that. So the answer to part B is this. Right. So 0.29 times 0.71 divided by 850, square root of the whole thing, and we get that. Part C. Any random sample of 850 adult Americans, what is the probability that less than 28% own a credit card? Okay, so we have the same sample size of 850. What this is asking us is, what is the likelihood that the proportion of one sample is less than 28%? Remember, every one of these little dots in this distribution represents the proportion of a sample of size 850. Okay, that's what this distribution does. So I'm just asking you, what's the likelihood that we get a value of 28 or less? So let's draw the picture with that and recreate that over here. A little more room. So this is normal. We know the mean of p hat is equal to 0.29, and we know the standard deviation of p hat is equal to 0.0157. And this is p hats, and we want to know what's the likelihood that we would get a value of 28. Let me exaggerate a little bit here. 28. So we want this blue area right there, 28% or less. Right? In a that less than 28% own a credit card. So we want that area right there. Okay. So what is the probability statement that we want to write? To find that, right? This is the variable, so it's the probability that p hat is less than 0.28. Oh, sorry, this is 0.28. 0.28 is equal to, and now this is a nice normal distribution, so this is just going to be a normal CDF from negative infinity through 0.28. with 0.29 as the mean and 0.0157 as the standard deviation. We can just punch that into our calculator and we're done. Distribution, normal CDF, a bunch of negative 9s, comma, 0.28, comma, 0.29, comma, 0.0157, close parentheses. I'm getting 2621. 0.2621. Okay, so that means that this area right there is 26.21%. Any questions? So there are two ways of interpreting this answer. One way is to say the probability that one random sample of size 850 will contain less than 28% people in that sample that do not have a credit card. Right? The probability that will happen is 26.21. Okay. The other way of interpreting this is that of all samples of 850, right, all possible samples of 850, approximately 26% of all of those samples will be samples where there are less than 28% of the people in that sample that do not own a credit card. Good. So Two ways to look at it. Both are equivalent. Any questions about the answer to part C? No? No? All right, part D. Okay, once again, now it says does not own a credit card. So, given that the sample size is given as 470, and we are told that in our sample, we know that 140 do not own a credit card. Do not own a credit card. So we want to know what is the likelihood that 140 or more do not own a credit card. 140 or more. Right? Do not own a credit card. So let's make sure you change that on here. Okay, so back to the original then. So we need to make sure that the two conditions are satisfied for this. So the first one is going to be that the sample size for 70 has to be less than or equal to 0.05 times the population of all Americans. Americans. Oh, that's fine. That's going to be fine. And then we also have to check that 470 times 0.29 times 0.71 is greater than or equal to 10. That's also going to be satisfied. We checked that already. We're good. Okay, now we've got to get the new standard deviation, which we saw before as well. So that new standard deviation of our distribution, sigma p hat, is going to be approximated by 0.29 times 0.71 divided by 470. Take the square root of that whole thing. We're still going to get 0.020, is it 9? Yes? You guys aren't helping me out. Is that right? Yeah. Okay, so now we know that our distribution of sampling proportions, p hats, is going to have a mean of p hat equal to 0.29, and sigma of p hat is going to be equal to 0.0209. And so our sample proportion that we get, sample proportion is equal to 140 divided by 470. So this is equal to 2979. So that would be a value on here, 0.2979. So this is the area we have there. And something like this or more is what we want. So a proportion that's that or larger is what we're looking for. So we know that this is a nice normal distribution. Normal distribution of sampling proportions, or sample proportions. Okay, so this area that we're interested in is going to be equal to the probability that p hat is greater than 0.2979, which is equal to normal CDF from 0.2979 through positive infinity, and with a mean of 0.29, comma, and a standard deviation of 0.0209. Now we're getting something a little bit more realistic or valid. 0.2979, comma, infinity, comma, 0.29, comma, 0.0209. 3527, 0.3527. So that means that this area right here is 35.27%. Good? Questions? What if I did want to write a word problem that did have does own a credit card, do not own a credit card? What if I want blank number or less number of people do own a credit card instead of do not own a credit card? So what we have to flip is this number as well to be a little bit more realistic. So 330 is the complement of that. So if I wanted to write a word problem that said what is the likelihood that my sample would have 330 or less or more, then we get like something a little bit more realistic to something we could possibly get, and then we get a more valid answer as opposed to getting almost 100%, which we were getting before. Do you see that? Good. So this whole thing could have been solved by either, so the mistake was that the original question said 140 or more own a credit card. So one way to fix it is to stick in the do not own a credit card here, and that fixes the whole thing. We have a nice valid question. Or the other way to fix it is to have said, well, we can just stick to leaving it as own a credit card, but we'd have to change this to 330, and you can either leave or more or less, and then get rid of the do not own, and then you can say the word problem could have said what is the likelihood our sample of 470 has 330 or less people that own a credit card. Good, and then it would have worked out. Any questions about that? Good. Sorry for the mistake there. All right, moving on then. Number 3. The running time of movies produced by Columbia Pictures approximately normal with a mean of 126 minutes and a standard deviation of 9 minutes. Find the 58th percentile. Okay, how do we find the 58th percentile of that one? What does the 58th percentile mean? /58th percentile is the number that separates the lowest 58% from the highest 42%. Okay, so our picture for this one will look like this. We have a normal distribution as was given to us. Normal distribution. The mean of the distribution is 126 minutes. The standard deviation of the distribution is 9 minutes. So this is some random variable x. And so the 58th percentile will be the value in this distribution that separates the lowest 58%. So that's x right there, such that this is 58%. That should be pretty easy, right? Well, let's use a instead of x, because that one's weird. Is that a? So a is going to be equal to int norm 0.58, comma 126, comma 9, right? The area to the left, the mean and the standard deviation of the distribution. And what do we get there? .58, comma 126, comma 9. 127.817. So 127.817 minutes is the value that separates or is the 58th percentile of this distribution. Okay, in the interest of time, I think I'm going to skip a couple that are easy here, or should be easy at this point. If one Columbia Pictures movie is randomly selected, find the probability that its running time is between 120 and 130 minutes. That should be pretty easy, right? What's that one going to be? Normal, CDF, 120, 130, mean and standard. Okay, yeah, that one's easy. Part C, if one Columbia Pictures movie is randomly selected, find the probability that its running time is less than 115 minutes or more than 132 minutes. Well, that one we're going to have to take two separate normal CDF functions for the left tail and the right tail, and then add them together, right? So it's going to be normal CDF from negative infinity up through 115 with a mean of 126, a standard deviation of 9. And then we're going to add that to normal CDF from 132 to positive infinity with a mean of 126 and a standard deviation of 9. Find those two separately, add them, and then you're in business. Okay, so that one should be pretty straightforward as well. We've already done the sampling distribution ones as well. How about we jump to confidence interval ones?
Same thing to log it to our portal page?
Yeah. Okay, so why don't we take a look at starting with number 5? Okay, so this one is about, when you read this class is a lot about word problems. The whole thing is word problems. There's very little arithmetic in here, and our calculators take care of a lot of the math. So we've taken away a lot of the arithmetic away in these classes. So what's left is these word problems, and so one of the most important things is to read it and identify what kind of question is this. Is this a chapter 6 question, a chapter 8 question, it's a chapter 9 question? What is it asking me to do? So that's the first thing that you need to practice when you're preparing for a test. On your homework, that's another thing that I think misguides people. They're doing their homework from 7.8, 7.3. All the questions are almost identical, and they kind of fall into a pattern of like, oh yeah, they give you the little p, and then you divide it by the little n, and then that's your answer over here. And so they kind of get formulaic as to where that's the answer. And then they go over to chapter 8.2, and again, all the questions are very similar, and you kind of fall into this pattern. But now you're on a test, and they're just sort of random questions given at you, and the first thing you really need to do is think about what kind of question is this. Are they talking about means, proportions, or standard deviations? Those are the only three things we really deal with anymore, right? We don't really talk about medians anymore. We don't really talk about the range values or the mode values. Like all those things we've sort of ignored and left behind. All we really focus on now is population means, population proportions, population standard deviations, right? Or dealing with the samples, the sample mean, sample standard deviation, and the sample proportions. Okay, so what parameter are we dealing with in this question?
Which one? Number 5?
Number 5. Let's read it. In a Gallup poll of 1,004 adults, 93% indicated that restaurants and bars should refuse service to patrons who have had too much to drink. Okay, are we talking about a mean? Are we talking about a standard deviation, or are we talking about a proportion? Proportions, okay. So what chapter is that? What section is that? 9, chapter 9.1, right? So right away we're already kind of categorizing it. And this is going to ask us to find the critical values needed to construct an 82% confidence interval. Okay, so what do we do when we have to deal with an 82% confidence interval? What are the values we need?
We need z values.
Use z values. We need to go to our standard normal distribution. And we need to figure out the values that track the middle 82% of the data. Okay? That's because they've asked us to find an 82% confidence interval. So in all of these questions, they give you this value. They tell you what confidence interval they want. Right? So we need to find this, z sub 1 and z sub 2, such that it traps the middle 82% of our data. Because it's the standard normal, we know the mean is 0, sigma is 1. Okay, and then because it's central, it's okay, so we know that this must be what percent?
100 minus, yeah, there you go.
Right, the middle is 82, so that means that the sum of the two tails is 18, which means that each one of these tails must be 9%, right? A little bit of, the distribution is symmetric, centered at 0, so that makes sense. Okay, so now how do we find these guys with our calculators? What do we need, which function do we need to use?
Inverse norm.
Inverse norm. Now, sometimes I just like to label them as z sub 1 and z sub 2, but also we could label them as z sub 0.09, that's fine, or z sub 0. What's over there? 91, right? I would be okay with either notation as long as you put it on your picture. The z sub 1 is right there, z sub 2 is right there, and then maybe off to the side you indicate what they are. So c sub 2 is equal to in norm. Okay, now remember the calculator always cares about the area to the left. So to the left we would find 91, 0.91 comma 0 comma 1. And so what do we get with that guy? Okay, so 1.3408. And now if you want to go back and find the other one, that's fine too. Z sub 1 then equals to in norm 0.09 comma 0 comma 1, that's fine. Or you can just say that it's symmetric and just say that it's the opposite sign of this one. We already know it's going to be negative 1.3408. If you at least show me one of these, I will give you credit. I know that you know that it's the opposite sign.
So, we don't have to do both?
You don't have to do both. On the test, I wouldn't require both. I do require one. One of them will be a point. Yeah.
So is that what it's asking for here? Because it gives you a spot for z,
Yeah.
but it's only one.
Correct. So just
I
one of them.
one.
So the reason that is because we're creating a confidence interval. Remember, the next thing you want to write down, though, or maybe even the first thing you want to write down, is the formula. Which, in fact, the formulas are all given to you, so you don't really have to memorize any of these. You just have to spot it and identify which one is which, right? So what is the formula we're going to need for finding a confidence interval for a population proportion? It is...
Wait for it.
P hat, right? We're starting with our sample proportion.
Square root of
Plus or minus z sub alpha over 2, square root of, there it is, okay? So there is the formula we need for finding a confidence interval for the real population proportion P. And so the formula only uses z sub alpha over 2. The formula only uses this one, z sub 0.09. It only cares about the one on the right because of symmetry, because we know that the opposite one is going to be the same sign, and because we're doing plus and minus, it actually turns out it doesn't really matter. You don't need both of them, you only really need one of them, right? The other one is the same one, just opposite sign, so the formula will give it to us. Okay? So now, in our word problem, or question, we were given the values for p hat. It said that in a Gallup poll of 1,004 adults, so we have that n is equal to 1,004, and we were given that our p hat value, our sample proportion, was 0.93. So we have everything we need already. We got the p hat value, we have n, therefore we know q, because we know it's the complement of this. So we know that q hat is going to be 0.07. And z sub alpha over 2, we just found it over there. Okay. So in the picture that you're given this kind of a distribution. This is what I'm expecting. Make sure you label this the standard normal as opposed to any other normal. So it's the standard normal, centered at 0, standard deviation of 1, and then some sort of z notation. Either z1 and z2, I'm fine with that, as long as you come over here and label them as well. Z sub 2 equals to this, or z sub 1 equals to that. Or if you want to do z sub 0.09, that's fine. Shading the appropriate region, the middle 82% in this case. Right? So that's what I'm expecting to get full credit for that little picture there on the right. So far we're okay. Now the next part says find the margin of error. The margin of error is the part that we add and subtract from the center, from our point estimate of p. This part right here is the margin of error. Okay, so on your way toward finding a confidence interval, you need that. So just find that, and then you add and subtract it from p hat, and that's how you'll get your interval. Okay, so I'm just kind of breaking down the process into little pieces and kind of guiding people toward the answer, as opposed to just saying find the confidence interval and giving you a big blank page and then expecting you to do everything on there. I'm just kind of putting some little clues here and there of what I'm looking for and what I want. That's why I put this empty thing there. Make sure you do some stuff there and get some points for doing that. And then this. So let's just plug in our values. We know that this is going to be equal to 0.93 plus or minus 1.3408 times p hat, which is 0.93 times q, which is 0.07 divided by 1004. Take the square root of that whole thing. So let's figure out what that is. I'm getting 0.0108. 0.0108. Okay, so that's what we call the margin of error. That's the thing we're going to add and subtract from the point estimate of p to give us our interval. So this will end up being 0.93 minus 0.0108. Our interval is going to be 0.93 minus 0.0108, comma 0.93 plus 0.0108, which is going to be equal to 0.9192, comma 0.9408. And that's our interval. Okay, so now a quick little statement. This is an 82% confidence interval. An 82% confidence interval for P. The population proportion is this interval, which is 0.9192, comma 0.9408.
Can you go back a second?
Okay, where? What
Can you
question?
explain to me why z sub alpha over 2 is equal to that?
Z sub alpha
why
over
is
2?
that notation? Why is that z sub alpha over 2?
Oh, remember that, here, we'll just go back here. You know, there's no reason for this other than that's what this author agreed to, and it's sort of commonplace, but the notation is this. If we have this as some area, say this is the area 0.18, it's 18% right there, then we call, and this is the standard normal distribution, then we just label this as z sub 0.18. It's the area to the right.
So, okay, so you said it's because alpha is both wings.
Yeah.
Alpha is both
Account
wings,
for just
exactly.
one of them.
Okay, yeah, so I was gonna get to that. Okay, so the notation for confidence intervals is that they give you 1 minus alpha in the center,
Okay.
right? It's the ugly notation. 1 minus alpha is in the center, which means that the sum of the two little tails is gonna be the alpha. Like if this is 82%, or say this is 80% in the middle, then alpha must be 20. Right? It's the complement of this, which means the two tails are 20, meaning that this tail is just 10 by itself,
Right.
and this tail is also 10 by itself, and so it's half of alpha.
Okay.
So the notation is just a little ugly that way. This is alpha over 2.
What is the point estimate?
A point estimate is our very best guess for the true proportion, where we guess it by one individual actual point as opposed to an interval. And so our very best guess is the proportion that we get from our sample, which is this guy,
So.
right? Like for example, if I wanted to guess what is the ratio, what percentage of stats students are women? What's in the entire country? What is it? Is it 50-50, or are they 50? Are they 40-60? What is it? Well, I have no way of guessing that, so I'm just gonna take a sample. How about you guys? I count 1, 2, 3, 4. Okay. So I count how many women there are in here overall, and that's my best guess. Now, is that a good guess? Well, depends. It depends on whether or not this class is a good representation of the entire population of all stats classes, or if it's not. I don't know. Point estimates are just one single number that you're guessing. That's my number. As compared to an interval guess. This is my best interval guess, that the real proportion in this situation is somewhere in here, and that's much better than just one number, right? Okay, so my point estimate is 0.93, and my interval guess is between 0.91 and 0.94. Any other questions? Okay, and then the interpretation of this, right? Don't forget what this means. So, if I asked 100 different people to go out there and get their own samples, their own samples from the distribution, it's possible, it's likely that almost all 100 people are going to come back with their own sample proportion, right? Probably different values. And so when they go into this equation and they calculate all this here, it's likely that we'll get 100 different intervals, right? Because they all have their own sample proportions. So if I ask 100 people to go out, they'll have 100 different samples, 100 different sample proportions, and so therefore they'll come up with 100 different intervals. So if all of them do everything correctly, I'm expecting that about 82 out of those 100 intervals will actually include the real answer, the real population proportion. Whereas I know I'm expecting that 18 out of those intervals will fail to include the true proportion through no fault of their own, right? This process, this 82%, is indicating that this process will give us an interval that really does include the proportion about 82 out of 100 times. And this process is going to fail to give us an interval that has the true proportion about 18 out of 100 times. Okay? So it's a very subtle difference as to say that there's an 82% chance that it's in there. It's not really that. That's not really the case. It's more of this is how often this process works, not whether P is in there or not in there. Okay, it's a very subtle difference.
So you want us to say that 18% that it's not, or 80?
I want to say you can compact what I said a little bit, but you have to be careful on how you choose your words. So I would start with saying that if 100 different, yeah, I mean something along those lines, I think is important. I think. Okay.
So, when you ask specifically on its own for the margin of error, all you're looking for is 0.0108 for that question?
Yes, for that portion of find the margin of error. This is the answer here, 0.0108. This is the margin of error. But I do want some sort of work shown. So this is the work right here. You don't actually have to. I think on the first test, because I said you must show your work, not just the calculator functions. I mean, that doesn't mean you have to multiply this by hand. Somebody like multiplied and added and took square roots by like the long way. I was like, why are you doing that? I don't mean that you don't get to do arithmetic with your calculator. Please do all the arithmetic with your calculator. But I want at least for you to just show me where it came from. Because there is some easy buttons in your calculator that find confidence intervals. I'm sure some of you guys have found them on YouTube and whatnot. And that's fine if you want to, kind of double check your work, but it's not good enough for me here. I like technology, but I think in those rare cases it goes a little too far, makes it a little too easy. It just asks you for, plug in this, plug in that, plug in the 82, and then boom, this thing pops out, and it's just too easy to get an answer. And it's hard to really know if anybody really knows what they're doing at that point. They're just plugging in what it asks them to do. And so you can double check your work that way if you like, but you still have to do it this way to get the credit. So
I'm sorry, what did you say the point estimate was?
point estimate in this case is this. It is our best one number guess for the population proportion. On the other hand, this is an interval estimate, right? Would you rather guess my salary and let's say there was a game where if you actually guess my salary, you win $1 million, but you have to be accurate to to within $1, okay? Would you like to guess one single number and hope that that's true? Or would you like to have a little interval and hope that interval, I think most people would agree an interval is more accurate than having one single number be your guess.
Can I redo my statement?
Yes, go ahead.
If I ask 100 individuals to get their samples, to get 100 different samples, 82 of the 100 will include, 82 of those 100 individuals will include an interval with the true proportion.
I would add into it that you ask them to create an 82% confidence interval.
So can you say the whole thing again?
If I asked 100 individuals to create their own 82% confidence intervals from their own samples, if I asked 100 people to go out and get their own individual samples and create an 82% confidence interval, I would expect that 82 out of those 100 people will get a confidence interval that really does include the population proportion, and 18 out of those 100 will come up with an interval that does not include it. That's I think it's the longest way of saying it, but I think it also really clarifies what I'm trying to say. Now there's ways to shortcut that. Now you could say that this 82% is as to how often this procedure will give you the correct result. So you could say 82% confidence interval means that 82% of the time this procedure will produce a confidence interval that does include it, and 18% of the time this procedure will produce a confidence interval that fails to include the true population proportion. No? You didn't like that one?
Can you say the first sentence one more time?
If I asked 100 people to go out and get their own sample and to create an 82% confidence interval, I expect that 82 out of those 100 results, 82 out of those 100 confidence intervals will really include the true population proportion, whereas 18 out of those 100 will fail to include it.
Do we need both parts of that? Can we
No,
just say
I think if you just
82?
say 82 out of 100 will include it, it's already built in that you know that the other ones do not. So yeah, so I was, like I said, my sentence is extra long because I really want to make sure people get that, but there's ways to shortcut that a little bit. What I don't want to see is people just saying that there's an 82% chance that P is in here. That's not what that means. Okay? There is not an 82% chance that P is in here. P is either in here or is not in here. This 82 refers to the procedure, how confident we are that this whole process will work. This 82% does not refer to the fact of P being in there or not being in there. Got it? We are 82% confident in the process, not in the answer. This process, this whole formula, this whole process leads to a confidence interval that works 82% of the time. Good? It's a subtle difference, I know, and I think some stat books just kind of give up on trying to express that subtle difference and just give up and say that there's an 82% chance that P is in there, which is sad. Anyway, any other questions on this one? No? No. It did take a while to answer, but I think most of that was not really in like the kinds of things you would need on a test.
So-
this is all the writing you'd need for the test question.
On the test, would you break it down like that?
Yes.
Okay.
So this is, a good idea of how I like to write these kinds of questions down and break them down. So,
I think it's helpful.
okay, well, good. Okay, let's move on to the next one, number 6. A quality control engineer wanted to estimate the mean weight in grams of plain M&M candy. The table below contains the weight in grams of 10 randomly selected plain M&M candies. Okay, so 10, there's a sample data right there. And they're going to ask you to construct a 94% confidence interval to estimate the mean weight of plain M&Ms. Okay, so is it clear that we're talking about what parameter?
Mean.
Means. So we're going to have to create a confidence interval for means. All right, so the first thing you need to do is find the, what's the first thing you do?
Oh, let's see. Graphic?
Okay.
Linear? No.
All right, so check the conditions. That's really good. Yes. Check the conditions that this will satisfy a sampling
Oh, and you have to
distribution.
find
What's
the
that?
average of the sample? The mean of the sample?
You got to find your sample information. You got to find the sample mean, sample standard deviation. Make sure that this sample comes from a population that's approximately normal. You also need to identify what the formula is, what the equation is for a confidence interval for means, right, of your formula sheet, which one's which one do we need? And then from that, you can kind of decide what you're missing or what you need. So why don't we start by finding the sample information. So put all that stuff onto list 1. Do a one variable statistics on list 1. We'll get our sample mean, sample standard deviation, and we'll take it from there. Meanwhile, let me write down this sample stuff. So.
But it doesn't go, okay. It doesn't go here, though, does it?
So put that all into your calculator, list 1, do a one variable statistics, and we should be able to get our sample mean and our sample standard deviation. And n is equal to 10. Okay, did we get the sample mean yet? 0.8 what?
91.7.
91.7?
No, 0.917.
917.
We got the
917. 917, okay, and then what's the standard deviation?
0.579.
0579.
That's it.
0579. Sorry, I didn't put that extra zero in there. Okay. 917. Okay, we know from chapter 8 that if we have this sort of parent distribution and we take a sample, we find the sample mean, and then we kind of graph that as one dot. And then we take another sample, get the sample mean, graph that as one dot, and we do that over and over and over and over again. Then all those sample means begin to look like a normal distribution, right? This is a normal sampling distribution. Oh, sorry. Normal distribution of sample means.
So, but when is it a t distribution?
Ah, good. That's why I was pointing this out. So I've deviated a little bit from what you need to write down. You don't need to write down this. I was just pointing out that when we have parent distribution and we graph all these sample means, then we know that this is going to be a normal distribution. Mu sub x bar is going to be equal to the same as this one, mu, and sigma sub x bar is going to be equal to sigma over the square root of n, right? We know that in general to be true. However, this is going to be a little bit different because we don't know that and we don't know that. So what are we doing? We're making point estimate guesses. We're going to guess that, well, since we don't know the mean, we're going to use our sample mean to be our very best guess for this. And we're going to use this, S, to be our very best guess for this. And that is what we're using to construct our distribution. Good? Now, when we construct our distribution, because we're making those guesses, it turns out that our distribution is no longer normal. Our distribution is very similar to normal, but just a little bit different. It's called a t-distribution. It's no longer normal. So it'll look very similar, a little bit different. T-distribution. Now, t-distribution is going to be centered at 0 there. Well, that's not true. It'll be a t-distribution, and it'll have its own mean and standard deviation. But the actual shape of the distribution will be a function of n. It'll depend on n. And so it'll have 9 degrees of freedom. Degrees of freedom equals to 9. Okay?
Oh, yeah.
Good. Okay. And so it is in this distribution that we need to work with.
So then we just use our standard deviation to solve for the new standard deviation right there?
Correct. Because we're going to guess this to be equal to that, we're going to use a standard deviation that comes from there. So it'll be sigma sub x bar will be equal to s over the square root of n, which will be equal to 0.0579 divided by the square root of 10. And mu sub x bar, we're still guessing it's pretty close to 0.917. So it's still centered in the same place, we still have that same thing. But here, sigma becomes s, and so we divide it by the square root of 10. And what do we get? 0.0579 divided by 10 to the 0.5 power. 0.01831.
Is this gonna be in the back of the book, the formula?
Yeah, it's like the formula for finding the new standard deviation of the t-distribution.
Okay, so I deviated a little bit, so let's go back to what you were actually supposed to write. So none of this is anything that you need to write on your test. So let me just go back to what you would really write. Okay, so we need the mean and standard deviation, so let's just write that in. Okay, so you found your sample to have
917.
917 bar. And we need S to be equal to
579.
0.0579. Okay, so then the next thing we need to know, why don't we write down the formula? That's the next thing I would do. And so the formula that you'll be given in the back of your book there is x bar plus or minus t sub alpha over 2 s over the square root of n. Okay. So I would identify that in your formula sheet, figure out which one's which, and I would write that down. So I know I need x bar, which I have. I know I need s, which I already got. I know n was given to me, n was
Wait,
equal to 10.
for the S, are you asking for the standard deviation of the
The sample.
first sample
Of the sample.
or of the the second one?
Well, we don't know the first one because we don't know anything about the population. So the only thing we have is the
That's
sample.
it.
Yeah, the only thing we have is the sample standard deviation, and we're going to use that as our guess for the population standard deviation. Right? We're replacing sigma with S because we have nothing else, to go by.
Okay.
Got it? That's what I was attempting to describe over here.
Then why do you have to do that formula for?
So when we know these two and we do a sampling distribution in chapter 8, this is the formula, sigma over the square root of n. And it's normal. But in this section, because we don't know sigma and we're making a guess about s, s is our very best guess that comes from our sample, and we're making a guess about this is another guess, which is our sample. These two things come from our sample, making two guesses. There's more variability in our distribution, and so it becomes a t-distribution.
Okay, but because we're working with the t-distribution,
Yes.
shouldn't sigma, are you asking for sigma on the other thing, for the new sigma?
Okay, so back to this guy.
Yeah.
The formula is this, right? Where this is the standard deviation of the t-distribution, right? It was s over the square root of n, s over the square root of n. And then t sub alpha over 2 refers to the standard t-distribution, and we want to find out the t-value, the multiple of standard deviations away from the mean that will trap the confidence interval that's required. Okay. Like, what's the confidence interval that they're asking you for?
So, okay, but
94%.
94%.
in the t-distribution, you still want us to solve for the new sigma, our new like right here. You don't want us to write the same one down from up here, right?
So let me move forward. No, that's the standard t-distribution. This is what you're expected to write on that answer sheet. So you haven't really written much. This, and this, and I'm gonna go to that now. Because I know I need t sub alpha over 2, I need to know which one I'm constructing, and I'm constructing a 94% confidence interval for mu. So that means I need to draw this. I need to go to t distributions.
It's barely gonna support.
Mu equals to 0, sigma equals to 1, and I want this. I want the area that traps the middle 94%. Now we have the standard t distribution. The standard normal is the standard t distribution. Right? This is not the distribution that comes from sampling. This is your standard t distribution centered at 0.
Okay.
Right? Just like when we have normal distributions. If you think back at what we did before, we have, oh, I thought it was over there already. When we were just working a little while ago, we did a sampling distribution for the 93% that refused bar service, right? And then that leads to a sampling distribution that's centered at 0.93. Well, that's different than our standard standard normal distribution centered at 0.
But then that's not a t-distribution.
It is. It's a t-distribution centered at 0.
But
The t-distribution refers to the shape of it, right? Remember, the horizontal axis is all possible outcomes of that variable, whereas the picture above is describing for you the likelihood of it happening. It doesn't describe where it's centered at all. There are lots of distributions out there. There are distributions that maybe look like this, like two humps, and that has a special name. So anytime you have a two-hump distribution like that, it has that special name. There are distributions that have, we looked at the chi-square distribution, so it's got this kind of a shape. So the t distribution refers to the shape of the distribution, not where it's centered. And it looks a lot like the normal. It's very bell-shaped. So just by me drawing it, it's hard for you to know that it's not normal. So you just have to label it. Did that answer your question?
Is this right here, you want us to do a t distribution?
Correct. So now on your test, this is on the right-hand side, there's this little picture. Label it as a t distribution, 0, 1. And it's 94% in the center because we want to get a 94% confidence interval. And so that means that this guy right here is t sub, okay, what is this guy here? That's 3%?
T sub alpha over 2.
Alpha over 2, correct. T sub alpha over 2, which in this case is 3%, right? The whole thing is 6. That means that guy right there must be 3.
Is it always going to be centered at 1? I mean 0, 1?
Yes, for the standard t distribution. This formula refers to the standard t distribution.
Where is it going to tell us in the problem that it's standard t?
Nowhere. You have to know that.
Nowhere the formula you're using is telling you that
Yes.
it's standard.
That's right. So if you want to use this formula, this refers to the standard t distribution. Just like in the one we did a minute ago, we were working with this, p hat plus or minus z sub alpha over 2,
That's the
p hat q hat over n square root of that. This was referring to the standard normal distribution, right? We went over and we found out how many multiples of the standard deviation you have to go to trap the percentage that you're looking for your confidence interval. Well, this one is referring to the standard t distribution. Good, 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 good. Okay, so now we have to find that, and now how do we find that? Same as, or similar to the t distribution, the normal distribution, we have the t inverse function. So t sub 0.03 equals to in t, and now it cares about the area to the left. Area to the left is 0.97, comma, and now this, normally we'd put the mean and standard deviation here, but our calculators are just not that cool. They don't work with us centering it someplace else. This is why we have to go to the standard t distribution. It doesn't ask you for the mean and standard deviation because it only works with one of them, the standard t distribution. So all it asks for is for the degrees of freedom. And so the degrees of freedom for this case we're working with was 9. So we punch in a 9 there, and then it'll give us the answer. Did that make sense?
explain.
Good.
To explain.
What? I still don't understand.
2.50.
What is it?
2.50.
2.15. Okay, you still don't understand what?
Why we did the work to find the standard deviation of a distribution that we weren't working with?
The other board was for me to just show you conceptually what we're doing. Like I said, you wouldn't be expected to do anything on the other board on your test. This is what I expect on your test. This is the standard t distribution with 9 degrees of freedom, centered at 0, 94%. We find that. And the reason you have to do it this way is because you can't find the other one. Our calculators don't work with another t distribution that's not centered at 0. Got it? Maybe, kind of, sort of. All right, let's just finish up. We got everything we need for our confidence interval now. We got the mean, we got the t sub alpha over 2, we got the s, we know the n, and so x bar is equal to plus or minus t sub alpha. Let me scoot this guy over here. X bar plus or minus t sub alpha over 2, s over the square root of n. So x bar, we found out to be 0.917 plus or minus alpha over 2, which was equal to 2.15, s, which was equal to 0.0579 divided by the square root of 10, right? And this, the part you add and subtract, this is called the margin of error. when I say find the margin of error, this is what I expect to see, and then you can crunch that out, see what number we get. So this is 0.917 plus or minus 0.3937. And so if we subtract it from that, we get the lower bound, and if we add it from that, we get the upper bound. 0.917 minus 0.03937, comma 0.917 plus 0.03937. 0.917 minus 0.03937 gets 0.8776, comma 0.917 plus 0.03937. This is 0.9564. So, and a 94% confidence interval for mu is this interval, 0.8776 to 0.9564. Okay, so this is all the writing I would expect, but obviously there's a lot of like concept stuff in the background as to why this is it and why it works this way.
That's the interpretation you want us to conclude.
Well, this is just a sentence about that. A 95% confidence interval for mu is this, but it's the same sentence or the same idea as before. If I asked 100 people to go out and have their own samples, then create a 94% confidence interval, I would get 100 different intervals because they will all have their own sample information. And I would expect that about 94 out of those 100 intervals will really actually include the real population mean, whereas 4 of those intervals will fail to include the real population mean. Okay? Now, this is not part of your solution, but I think maybe, hopefully, I'll address your question about this.
So the point estimate is 0.94?
94 or is it 93?
0.94.
0.94, okay. Whatever this, oh no, point estimate, wasn't it 0.917? 917?
Oh, it's the mean, right?
The point estimate is your best guess for the population mean, which is equal to your sample mean. That's a point estimate. Our interval estimate is the confidence interval. Okay, so maybe this will answer your question if I put this way. Let's put, and this is not part of your solution on your test, I think you're having still a little bit of difficulty
So
with this.
all t distributions have a mean of 0 and a standard.
No. Here, that's not either.
The standard
Okay.
t distribution.
So let's say that I have a parent distribution that is normal, and we know the mean in the sigma. When we do a sampling distribution, we take a sample, we find the sample mean, we graph it, grab another sample, we graph it. We know that's normal, right? That's from chapter 8. If this is normal, if we know that and we know that, it's going to be normal, and it's going to be centered at 0.91. So it's going to come over here, and it's going to be here, and it's going to be normal. Okay, there it is. Now, on the other hand, since we don't know that, and we don't know that, we're making guesses. Because we're making 2 guesses, then this is no longer a normal distribution. This is going to be a t distribution, and the t distribution might look a little more like this. Okay, so this guy is a t distribution. T distribution. Okay, and they're both going to be centered at mu equals to 0.917. And now the t distribution is going to be a little bit different than the standard deviation of the normal one. And it's going to have the s over square root of 10 value, which was 0.0, what was it? Did we, or we didn't write it down?
0.03937.
3937?
Yes.
Was that, wait, was that S over,
Oh, wait.
no, that's this thing. So it's just this part. It's 0.0579 divided by,
0.18,
no, it's point, yeah, 0.1831,
31.
1831. Okay, so that's our sample standard deviation of 0.579 divided by the square root of 10, which gives you 0.1830. Okay? Are you still with me so far? Yes? Still with me so far?
I'm just not understanding, so. in
I'm
this-
not done with the explanation. Just give me 1 second and then you can say that you're still confused. Give me 1 second. We do this distribution, we get this t distribution, and now we want to find out the middle 94% of this data. We want to find this stuff right in here that gives me 94%. 94. Okay? And if we had a really cool calculator, we could just type that in. We know that this over here is 3%, and I know that this is 3%. Right? If we had an awesome calculator that said, let me put in t of 0.03 with a mean of 0.917 and a standard deviation of 0.1830 and degrees of freedom, sorry, the degrees of freedom was equal to 9. If we can type all that in, it would just give us that number right there, and we would be done. But we don't have that. Our calculators cannot do that. So what do we have to do? We have to go back to the standard t distribution, which is centered at 0. It's a t distribution. Now remember, the t just refers to the shape. So this shape right here is the same as this shape right here, except it's centered at 0. With degrees of freedom equal to 9. Okay, and so now here we figure out how many standard, I said something different. Yeah, okay, so here this is centered at 0, and we're going to find out how many multiples of the standard deviation you have to go away from the mean in order to trap the middle 94%. That's what that t sub alpha value is.
And then we take that number and we add it to our mu on the other side.
Alpha over 2. And that tells us how many multiples of this thing I have to go in order to trap the middle 94% in this distribution. So over here we found out this was 2.15, I think.
Yeah.
2.15. Okay, so I have to go 2.15 multiples of sigma in this distribution to get above and below the mean to trap the middle 94%. Which is why over here we have to go plus and minus 2.15 multiples of this to trap the middle 94%,
So.
and hence the formula.
Okay, so whenever we use a t distribution, we always, unless we're, you said, okay, so because our calculators don't do that,
Yes.
we always have to
Yes.
use the standard t.
Yes.
So in any time that we draw a t distribution, it's going to be standard t, and it's going to be 0 and 1 for the mu and the,
How
How do you want us to?
I don't want
write
to
it
say
on the test?
always is such a some limiting
for
thing.
this test.
How do you want?
In
us
these
to
questions,
write
when I ask you for that, yes,
And
that's
you
what
want
I'm
us to
looking for
say
right now.
it? You
Standard
want us to
T.
just put?
Yes, standard t
0 and 1?
distribution. Yes.
Okay, because we find the new sigma in the formula.
Correct. The formula. Now, if we go back to what you actually write down. The equation for this thing has the standard deviation of the distribution we want, and we just multiply by the multiples that we get from our standard t distribution to get that distance.
Okay, so if we're finding the confidence interval for means, we know that we have to use the t distribution, and if we're not given, since we're not given those two, we know that we have to use the standard.
Because are limited by our calculators, right?
Okay. I
Okay.
understand.
Any other questions on this? No? No? Okay. All right, let's look at the last one then. The last one is on confidence intervals for population standard deviations. So it reads that a jar of peanuts is supposed to have 16 ounces of peanuts. The filling machine inevitably experiences fluctuations in filling, so a quality control manager randomly samples 12 jars of peanuts from a storage facility and measures their contents. She obtains the following data. So there's a bunch of data given to you, and so now we know we have to construct a 98% confidence interval for the true population standard deviation. That should already trigger the idea that we're working with chi-square and chi-square distributions. Okay, so the first thing we'd have to do is punch that information into our calculator and find the mean and standard deviation of those results. Also, you might want to start thinking about the formula for the confidence interval of a population standard deviation. So type those in and let me know when you're done. Questions? Okay, so here's our sample. We use our list one variable statistics. We can get our sample mean and our sample standard deviation, which are what?
15.8925.
Okay, and what's our sample standard deviation?
0.3492.
3492? Yes? Okay, so we need to work with a chi-square distribution. Remember, a chi-square distribution is this. Chi squared equals to n minus 1 s squared over sigma squared. And it looks like this. Chi-square distribution. And they ask us to construct a 98% confidence interval. So we need to find the values that trap the middle 98%. So that means that this right there is 1% of the data. And that means that that little tail is also 1% of the data. And so we need to find a chi-squared value there and a chi-squared value there. So this, remember this notation refers to the area to the right, so this would be 0.01, whereas this notation refers to 0.99. Now I just like to do chi-squared left and right in these kind of situations. That's just me. Chi-squared left, chi-squared right.
Can we write it like that?
I would be fine with that, yeah. But just make sure you put it on your picture, chi-squared left, chi-squared right. Okay, so here's our probability distribution. Now these things, again, if you have a really cool calculator, you can work on it and find it just the way we did the other ones. Inverse norm, inverse t, inverse chi-squared. Some calculators have that. Even if it doesn't have it, there's a software update you can do that you can install that program onto your calculator if you'd like. Or I think most people are just not going to have it, so we're going to have to use our tables for that. So you will be given a chi-square distribution table for this section, for this purpose.
Okay.
Okay?
And
So
in those
you look it up in your table. Yeah, go ahead.
Can you show, or no?
Okay, so the thing that we care about, remember, just like t-distributions, chi-square distributions, the shape themselves also changes just a little bit based on n. And so we have a degrees of freedom equal to 11, right? And that's because n equals to 12. Degrees of freedom is always one less than the sample size n. So we'll have to look it up in our table. Do you guys have it?
So it's the
Tables?
degrees of freedom and then the x2 value or whatever percentage.
Here, let me show you what that looks like. So if you have your book, go in the back. You got to find chi-square distributions.
What is this x2, I mean, x,
Oh, chi-squared. So I'm looking for either of these two. So you can either as chi-squared L or chi-squared right. Or if you want to use chi-squared 0.99 and chi-squared 0.11, either of those two would be fine.
But because these values are different, we have to have both, right?
Oh, correct, yes. So this is not symmetric about 0, so you can't just say it's the opposite sign or anything like that. So you can either choose to use this notation of 0.99 and 0.01, or I would be okay with the notation of left and right, either one. But in that step, I'm just asking you to kind of gather all the information you're going to need. So you just have to look that up in a table, which I will show you in a second right over here. There it is. Okay, so chi-squared says area to the right, so be careful with the various tables you get. Sometimes they switch it up on you, but this one's area to the right, and then you just got to look up which area you want to the right. So we want 1%, for example, and we want 99%. And then you got to go down and identify where the degrees of freedom is. So here is 11 degrees of freedom, 99%, and 1% with 11 degrees of freedom at 24.725. So this guy is that guy, which is equal to 24.725. And this guy is this guy, which is equal to 3.053. Okay. Questions? No? Okay. Okay, so now remember that if we did have a sigma squared, if we knew it, we can calculate the chi-squared value of this particular sample, and then it would land somewhere in here. right? What are the odds that it would land between these two values? Well, there's a 98% chance that it would land there. So then we did that whole thing with the inequalities last time, where we get to play with those inequalities and eventually get the sigma by itself, and that leads to the formula. So the formula we need for this is n minus 1 s squared over chi squared right, square root of that whole thing, less than sigma, less than n minus 1 s squared all over chi squared left, square root of that whole thing. Good. Right? That's the formula we came up with. That's the interval. This is the lower part of the interval, that's the higher part of the interval, and it traps the sigma. And we have everything we need. We know s, we know n, we already found our chi squared left and chi squared right values. So we're in business. We're ready to punch it in here. So it'll be 11.0.3492 squared all over chi squared right, which will be 24.725. Square root of that whole thing, less than sigma, less than 11 times 0.3492 squared all over chi squared left, which is equal to 3.053, and then we take the square root of that.
Are these also, the formula also going to be?
This guy is given, yeah, some version of that is given in the formula sheet.
So, why is left on the right side again?
We talked a whole lot about that last time.
I can't remember.
Remember when we solving and we flipped the fraction, that whole thing?
We're going to flip it, or we did.
This is the final result already. I mean, I went through that whole explanation before as to why we ultimately get this answer, but in this case, you're not expected to do that on a test. You just got to go right to your equation and find it from there, which is why I didn't do it here.
On your formula sheet, do you know what notation it uses for the chi squared? It just says left and right? Or what does it say on
I think it'll say alpha over 2. Probably it'll say chi squared alpha over 2, the same notation as before. This is the same thing as chi squared alpha over 2, the right one. And over here, this one will say chi squared 1 minus alpha over 2. Right, so this will probably say, so that's why I like to think of it that way. Now, if you get confused, again, this notation is a little confusing. When you look it up, well, you know it's 11 degrees of freedom, and you know it has something to do with 99% and 1%. And then when you put them on this table here, on this graph, well, it makes sense that the 3 is over here and the 24 is over there, right? It wouldn't make any sense for these to be backwards. This is a number line, so 3 has to be over there and 24 has to be over there. That's one way it would make sense. The other way it should make sense is that what happens when you take the same number, see these two are the same number, and then we divide one of them by a number that's bigger and a number that's smaller. When you divide by a bigger number, the answer is smaller, right? So putting this big number, this chi squared right, putting this big number here will make this side small. Putting this little number here will make this side bigger. So, you know, if you make a mistake, you're just going to get a silly inequality that 0.5 is bigger than, 2. And like, that's not true. So then just, you made a mistake and flip them back. So this would be 0.3492 to the power of 2 times 11 divided by 3.053 to the 0.5 power. All right. So this is equal to 0.6628. Is that what other people got?
So that's the confidence interval.
Yes.
And for this one, do you like us to write it like that? Or do you
So,
want to comment it out?
to wrap it up, a 98% confidence interval for sigma is, and then this is the lower part of the interval, 0.2329, comma, 0.6628.
Okay.
So that's, just a nice full sentence of what you found. A 98% confidence interval for sigma is this. And if you were asked to interpret it, it's the same interpretation as always. This percentage, this is a percentage of how often this procedure will give you an interval that actually includes the real answer. So if I asked 100 people to go out and create their own sample and come up with a confidence interval based on this formula, then 98 out of 100 of those people will come up with an interval that really does include the population standard deviation, and 2 out of 100 people will come up with an interval that does not include the real standard deviation, right? And it all goes back to the variation in samples. Sometimes you get a sample that just happens to be so far off from the original population, it doesn't represent the original population very well at all. And so in your particular confidence interval, because it's based on a sample that's so far away from the real answer, it will fail to include the true population standard deviation. Good? Questions?
Part C. Yeah, it's letter C.
Okay. The quality control manager wants the machine to have a population standard deviation of below 0.2 ounces. Does the confidence interval validate this desire?
No.
Why not?
And a standard deviation below 0.2?
0.20, correct.
Because it's less than the lowest interval.
Exactly. It's not in this interval. This information seems to be saying that he's wrong. Now, is it possible that the answer really is 0.2? It's possible, but it's unlikely, because we are 98 out of 100 times this whole procedure will produce a confidence interval that really does include it. I'm thinking this might be one of those 98 times, right? And it just doesn't include it. It's unlikely that this interval is one of those 2 times, right? You got to ask yourself, is this one of those 2 times out of 100 where you'll get an interval that fails to include it? Maybe the real answer really is 2%, and this is one of those 2 out of 100 times that we have an interval that fails to include it? Or is it that this is one of the 98 out of 100 times where it does give you a valid interval that does include the standard deviation, and clearly 0.2 is not in there? Right? So it's possible, but highly unlikely. Very unlikely that the real standard deviation really is 2.
So for this specific question, does the confidence interval validate this desire? It's enough to say no because it's not included in the confidence interval?
Correct.
Okay.
Since 0.2 is not in my 98% confidence interval, it is unlikely, though not impossible, it is unlikely, highly unlikely, that the real standard deviation is 0.2. We're pretty satisfied that it's not because of this 98% confidence interval.
Okay.
Good?
Good.
Questions?
Great.
Okay, so that was it. See, there's not, if you go right to it, there's not that much, but, behind every little thing, there's a whole lot of thinking and a whole lot of machinery in the background, so that's why it took so long to get through these chapters. But I hope it doesn't take that long to go through these tomorrow. We did 3 of the hardest ones now in an hour, with a whole lot of extras that aren't really anything you need to write down or anything, so.
No promises.
No promises?
Might take
Can
us as long.
I have you rewind just a moment, that it's very unlikely, and then
It's very unlikely that the true sigma value, the true standard deviation, is 0.2, because 0.2 is not in this interval. Because 0.2 is not in my 98% confidence interval, it is highly unlikely that it really is 0.2. Though it's possible. It is possible. It could be that this interval just fails to include the real sigma, which the sigma might be 0.2.
what did you say about standard deviation?
What about it? Sigma is the standard deviation.
Okay.
Yes.
The homework for 8 and 9 is not going to be due in the quizzes until Monday night.
Yes, I just changed that a little while ago. If you haven't noticed, but the last couple of hours I've done it. Okay.
Okay.
All right. So I'd like to get started on 10. so we can have enough time to really dive into that and cover a good part of it. 10 is a good review anyway of normal distributions anyway, because as you see, there's very little that's new as far as the distributions and the math and all that. A lot of it is very repetitive. It's just putting it in a different kind of context, working with hypothesis testing.
So are we not gonna have time to ask homework questions?
I'd like to get a little bit of 10 done, and we'll see how far we get into that. And then, you know, depending on how much progress we make, maybe we can, you know, pause 30 minutes. What time is it? 7 now. We have an hour and a half. Maybe we can do an hour of that.
Okay.
How many? Is there a lot of homework questions on what chapter or sections?
I don't know, I have to log into my thing. I think I only have one question though.
Oh, well then that shouldn't take 30 minutes.
Okay.
All right.
Wow.
Do you guys have a lot?